to my talk, the next to last talk today. And we had a lot of stuff that's coming up in the next 20 minutes already, like abstract syntax trees and deadlocks, and something I will add to the mix that you can do with OCaml is robots. And this is joint work with Stefan Bedeng from OUD, Florian Pichelmeier, who's with me in the back row there, Christian Buckel and Alois Knoll from the TUM, from the Robotics and Embedded Systems chair. And this is work that we're doing for OUD, so this is a real application and has a real use. So the outline is, first I'm going to talk briefly about what is an industrial robot system and what does it do. Then I'm going to talk about formal verification, how we're going to try to find bugs in the programs that control these systems. I'm going to highlight the results that we have so far. Then I'm going to go into a little bit of what OCaml code we use and two highlights from our code and something that we supply as open source. Then I'm going into how our experiences with OCaml are and what OUD thinks about that, and then I'm coming to a conclusion. So first, the industrial robot systems. The industrial robot systems that I'm talking about are the car body welding stations. These are the most highly automated systems that you can have with a car manufacturer. And they're highly automated up to 90% or even higher. So there are not very many people there and everything is automatic. And if you go in there, this is a huge robot ballad. And you have these car bodies just going through, and one robot is welding and one putting his door on, and then one is fixating that and doing gluing and everything. And so they seem highly automated, or they are highly automated, and they seem very complex, but this is, I think, for us in here, more from a mechanical standpoint, not from the software standpoint. And they do a lot with that. They have different car models on the same line, so if you, I don't know, if you order your next A3 and you order the sports bag and, I don't know, two-door version and I don't know what, then they produce it just on demand on the same line that they produce, I don't know, the four-door version of the A3 or something like that. And the downtime is extremely expensive. You can measure that by, if you would currently order an Audi, or I think this holds for BMW or Daimler, you would wait, I don't know how many weeks currently. And basically, if they don't produce a car, you will wait another week longer and they didn't sell a car. So, and the robot cells themselves are mostly grouped and are in groups of up to 12 robots, or something like that. So this is a distributed system we have to look at. So we're going more to the computer science standpoint. This is a topology of such a cell. You have several robots in there and one PLC. For those that don't know, PLC, it's basically an industrial computer with a not so nice programming language on there. And this is a distributed system. Every robot has its own computer. They are talking over a bus system to each other. And as with all distributed systems, you have the problem of shared resources. And in this case, it's very delicate because one of the shared resources that you have is the actual physical space. And if you have two robots that don't handle that correctly, you have a crash. So you can have deadlocks between those robots, like real deadlocks that your plant is not moving anymore, and you have the other race condition is a crash, which is not very nice. So the language that is running on the robots, this is the VCAR-C language. This is from KUKA. It's a very crude language, or I think for us here it's a very simple language also. It's an imperative language. You have these assignments. You then have a shared memory, or a fake shared memory between all the robots and the PLC. So to send a message to someone, you just set a variable. And then you have a goto and a label. You have subroutine calls. So these are not functions. There's not much stack in there, and they don't have parameters. So you call a function and you can give a condition if this function is called at this moment. Then you have something like a for loop, and you have a blocking wait expression. And the most important command probably are the movement commands that say, okay, and now on the current position we're moving to the next position. So the path that the robot actually moves most of the time is a fixed one. So if it gets a signal like start, it will move a concrete path, then activate its welding gun, move along a line, do its welding, deactivate the welding gun, and move somewhere away. And you can have, of course, you have some control flow in there, like for example, when the robot detects that the welding gun is not working so good anymore, it will go to repair station, for example, and will get the welding gun repaired. So, so how do you find the bugs in there, or what kind of bugs do we have? I already told you. Our main problem is like termination. It basically works like that. Your car body moves into the station. The PLC says to all the robots go, and they move in there, do their welding, and then they move out. And when every robot says, "Okay, I'm done," the PLC will say to the train station that where the car body is on, "Okay, move to the next station, move out." And so, if you have a termination problem, every robot must come to its final state of its program. Otherwise, you have an error in there. Most probably, it's a deadlock. And the other thing is, of course, as I already told you too, the freedom of collisions. And what you can do is, as the paths are fixed, you can look at the path of all the robots, and you can see which parts of the path would lead to a collision. Like you have, okay, we have the next movement command, and it will move the robot another, I don't know, 20 centimeters in that direction, by that in that way. And for that concrete path, we can determine if the robot can collide with another part of the path of another robot. And so we get a table of potential collisions out there, and together with the termination and some other errors that are not so interesting, we can create a claim that we say, okay, the robot 1 must never move from point 1 to point 2, while the robot 2 is moving from point 2 to point 3, for example. And we can do that for all the robots, and then we have a claim, and we can say, okay, we have a distributed system here, and it must always obey this claim. So how do we do that? What you often have in people that are using formal methods is that they take one system, and what they actually do is they create manually a model for that system. They use their model checker or their formal verification tool, and they show you that there's no bug inside. And then the expert moves on to, I don't know, some other department, some other company, and so on, and you're done. You know that you could formally verify everything like that, but not in the large scale, like for every plant. And this is the main work that we actually did. Is we created several compilers and generators that can generate this model that we want to verify from the information that we actually get from OUD. So we have some information, some base data about the plant, how many robots are in there. Then in the middle, the collision claims that I showed you on the previous slide. Then some interlock metrics. We need to know which robot uses which lock with which other robot. And then we have the control programs. This is one is the one from KUKA that I showed you the language of just on some slides ago, and the other ones are from Fanuc, but they look very similar. And what we have is we wrote, this is all OCaml code then, the programs down there. We have a little library, the Promula library, that basically has data types for an abstract syntax tree of a Promula language, from a Promula program. And the Promula language is the language the spin model checker uses. So you can think about Promula as C without pointers and without everything and without floats, but with threads. And you can put a Promula program into spin, and it will say you in the end, if you don't run out of memory, that everything is okay or that there's an error in there. So all these, the red programs, they all use this library to generate a part of the model, and then we just serialize the data to disk. And the yellow ones are all serialized, OCaml data from this library. And then we have something like a linker that collects all these parts of the model and fuses them together. So we say, oh yeah, the library, the variable of that robot is actually the same as that robot on the shared memory. And we tell that to the linker, and then it can produce one model. And what we do with the model then, we have some more I/O data that, for example, data that always comes from the PLC, like all security doors are closed, for example. We set that very explicitly there. Then we have a little optimizer that can throw out unused variables, like, okay, you're writing to a variable, but no one else is reading that. We can omit that assignment. And then we can actually create the promoter text. This is a box in the middle down there, and put it in the spin. And then spin will either say, okay, everything's all right, or it say, okay, there's an error in there, and then we go and make actually a back projection with the original robot programs and generate a system trace out of that, so the robot programmer can actually understand what went on. So this looks like that. This is a HTML application that we generate, also with an OCaml program. You have these tabs in there, and this is more or less a replay debugger where you can click through. Of course, there's only one path, and you can't do anything about it anymore. But this is very neat because it's only one HTML file, and if you have, for example, the robot program is from a third party, you can just send an email to a third party and say, oh yeah, there's a bug in your robot programs I just found, and here's a trace. So the results, here's some benchmarks. This is the time in here is only the time that spin takes, so the compilation before will also take some minutes. And for a lot of those plants, this succeeds, and we have success up to stations up to size of 9 robots. With 10 robots, with that one, we ran out of memory actually, and we had 64 gigabyte for that. So this is getting pretty tough, with at least with that model checker. And we could prove that some plants are deadlock-free actually, and we could also show some deadlocks. And one of the deadlocks that we found was a systematic one that was actually in the standard library of the robots. And to understand that, the normal locking procedure works like that. You have the robot 1 and it requests a token from the PLC. This is like if you have a cheer circle of kids, yeah, and you have like a ball, and only the kid that has the ball actually is allowed to talk. And this is this token that you get from the PLC. So when no one else has the ball or this token, then the robot 1 will get it, and now he's allowed to change the locks, if of course no one else has taken the lock. So what it can do, if it's free, it can lock the area that it has shared with the robot 2, then it can get away this token to the PLC, and sometime later when it's moved out, it will unlock the area. So what went wrong? The standard library actually allowed the locking of several locks at once. And the combination of how it was implemented and how the robot programmers were told that they had to use it could lead to this, that if both robots request 2 tokens that they have with each other, they wouldn't wait for the token to arrive. So if robot 1 will send request token A, the PLC will give it to him. Then robot 2 would come along and will request token A and B, and don't wait for A to arrive. And it's just a race condition here, and the PLC will say, okay, token B isn't handed out yet, here it is. And then the request from robot 1 will come for token B, and the PLC will say, ah, no, it's already handed out. And then both robots will only start waiting actually for the tokens to arrive. And of course that will never happen, so they have a very classic deadlock. And yeah, we found that bug in their standard library. So it was a very systematic bug. So for our OCaml code, what we actually use, aside from OCaml itself of course, is we use man here. This is a really great puzzle generator, especially since we didn't have a formal grammar of the robot programming languages. This helped a lot. Then we're using OCaml graph. We're using that for the control flow graph in our compilers and for the code analysis there. Another very important library is, if you work with engineers, is the comma separated value library to read actually data that you get from the engineers, which is most of the time in Excel. And what we started using bold, we're using XLib. This is more for historical reasons. We started with the standard library, and then someday we needed a little bit more, and then XLib came along. I started using Qtest from batteries. This is very neat, and this is on my wish list that this will become a separate tool. And we started using Oasis to release our code. We released the Promler library under BSD 3 clause license. It's on OCaml Forge. Then we have a Boolean expression simplifier. We also released it on OCamlForge, and we supplied some modules for OCaml graph, namely the fixed point, linearist, and contraction algorithms. And how much I have left? Like 2 minutes? Okay, then I will speed up. I will leave that alone. But I will show this because it's so nice. This is the fixed point functor that we have for the OCaml graph library. And this is very neat for data flow analysis. So if you use OCaml graph as your control flow graph, you can get an implementation of the word list algorithm actually, and with this functor. So what you have to do is to say you have to provide the types from your graph. This is so the very first type vertex, edge, and G is absolutely clear because those are the types of your graph. Then you have to specify the type of information that you want to have at each node. This is the reachability. This is like I think the cheapest data flow analysis ever. So you have at each node you have a Boolean. Is this reachable from the root node, yes or no? And then we give the direction, and this is a forward direction. We want to know if it's reachable from the start node. Then we have to specify an equal operation when the data is equal. This is very cheap. Then you have to specify a join operation, like when you have control flow joining, and the node afterwards will be reachable if either of the previous ones is reachable. So there's an OR, and the analysis is basically, okay, if my the previous node is reachable, so is my successor one for one edge. And then this will compute the fixed point for that, and you get this function down there. You can say, okay, analyze, then you have to give it a predicate, what actually is your root node, and your graph, and then you get a lookup function for every node where you can see is it reachable, yes or no. And of course, this works very nicely with the more complicated data flow analysis. I think it's not the fastest one, the fastest implementation on Earth, but you can write it down very nicely. So, for our experiences with OCaml, on our team, we have a strong, I think it's not so big, but it's very strong OCaml community at TUM. This helps a lot. We don't use any object orientation so far. We have, I have a plan for using first-class modules, and Florian has thought about using GADTs, of course, for the compilers. We're trying to write pure code, so side effect-free code all the time, and this actually helps a lot for refactoring, for the type system, and with the pure functions, refactoring is very, very nice. And what is actually hard is finding students at TUM for OCaml programming. I don't know what happens with them, if they're all going to, I don't know, if they prefer graphics over formal verification, or if they prefer Java over OCaml, I don't know. The experience with Audi, with our industrial partner, is that the Audi management, they care about results and economy. So if it works with OCaml and you can show that your stuff works, they don't really care about that. They don't micromanage you. And the people at Audi, the plant engineers, well, they're engineers. They are mostly mechanical engineers or mechatronical engineers, and so they're not computer scientists. So they don't think so strongly about their programming language. You don't come there and they say, we're doing everything in Java, because they're not programming all day long. So it's actually easier in that environment to say, okay, I'm using that language, and they say, well, okay. Yeah. And also it's a research project, and you can get away with a lot more than that. So for my conclusion, with this project, we found multiple deadlocks error, even in the solid library of theirs. So this is quite a success. We've shown that formal verification in this setting can even be cheaper than the testing, because the testing is enormously, comes with enormous effort. You either have to build a huge model in your computer, or you can only do the testing on site, which is even more expensive. And it is an option for analyzing these plants, and no one has done this before for these distributed robot systems. And in my personal opinion and of my team is that OCaml was a very, very good choice for that. I started initially with C and Java, and this was hell. And if you want to read more about that or are interested in the more in the scientific aspects, we also have a paper from on the last year's SPIN conference. You can read more about that there. Thank you.